In this slide, we will discuss the concept of synchronization in Java and why it is necessary. Synchronization is the process of coordinating multiple threads to control their access to shared resources. In Java, synchronization is necessary to ensure thread safety and prevent race conditions. Without synchronization, multiple threads may access and modify shared data simultaneously, leading to unpredictable results. To achieve synchronization in Java, you can use the synchronized keyword or explicit locks. Now let's look at a code example to understand synchronization in Java. Here we have a class called synchronization example, which has a count variable that is shared by two threads. We want to increment the count by 1000 using each thread. To achieve synchronization, we use the synchronized keyword in the increment method. This ensures that only one thread can access the method at a time, preventing race conditions. In the main method, we create two threads, thread 1 and thread 2, each calling the increment method 1000 times. We start both threads, wait for them to finish using the join method, and then print the final value of the count variable. Since synchronization is applied, the count will always be 2000. In multi-threading, thread safety refers to the concept where multiple threads can access shared data without causing data inconsistencies or unexpected results. It is important to ensure the correctness and reliability of multi-threaded programs. Data race occurs when multiple threads concurrently access shared data and perform read and write operations on it. This can lead to unpredictable output, data corruption, and program crashes. To avoid data race and achieve thread safety, synchronization mechanisms such as locks, semaphores, and monitors are used. Let's take a look at an example code snippet to understand thread safety. Here we have a class called thread safety example. It has a shared counter variable which is accessed by multiple threads. To ensure thread safety, the increment and decrement methods are synchronized using the synchronized keyword. This means only one thread can execute these methods at a time, avoiding any data race. By synchronizing the methods, we ensure that any modifications to the counter variable are atomic and consistent. In Java, the synchronized keyword is used to synchronize access to shared resources when multiple threads are accessing the same resource concurrently. There can be race conditions where the data gets corrupted. To prevent this, we can use the synchronized keyword to ensure that only one thread can access the resource at a time. When a method or block of code is declared as synchronized, it creates a lock on the object or class. Only the thread that holds the lock can execute the synchronized code, while other threads wait for the lock to be released. Let's take a look at an example code snippet that demonstrates how the synchronized keyword can be used to synchronize access to shared resources. In this example, we have a class called synchronized example with a private counter variable. We want to increment this counter by two different threads concurrently. To ensure that the counter is updated correctly, we use the synchronized keyword for the increment method. This means that only one thread can execute the increment method at a time, preventing any race conditions. In the main method, we create two threads and start them. Each thread will call the increment method 1000 times. After both threads have finished executing, we retrieve the final value of the counter and print it to the console. This example demonstrates how the synchronized keyword can be used to synchronize access to shared resources and ensure data consistency. In this section, we will explore the concept of locks, mutex, and critical sections for synchronization in Java. Locks are a mechanism that allows multiple threads to synchronize access to a shared resource. A mutex, short for mutual exclusion, is a type of lock that ensures only one thread can access a shared resource at a time. Critical sections are specific code segments that need to be executed exclusively by one thread at a time. Synchronization in Java helps prevent race conditions and ensures thread safety. Let's take a look at an example code snippet that demonstrates the concept of locks, mutex, and critical sections in Java. Here, we are using the reentrant lock class as our lock implementation. In the perform task method, we acquire the lock using the lock method and release it in the finally block using the unlock method. The critical section code is where we perform operations that need to be executed exclusively by one thread at a time. In this slide, we will discuss techniques for thread communication and coordination using the wait and notify methods. Now let's look at an example code snippet to understand the techniques for thread communication and coordination using the wait and notify methods. In this code, we have a class called thread communication demo. Inside the main method, we create an instance of a processor class. We then create two threads, a producer thread and a consumer thread. The producer thread calls the produce method of the processor class, and the consumer thread calls the consume method. Both methods are declared to throw interrupted exception, so we need to handle those exceptions. We start both threads using the start method and then use the join method to wait for both threads to complete before the main thread continues. In the topic of synchronization in Java, we focus on identifying common synchronization issues and how to avoid them in Java programs. 1. The first issue is race condition, which occurs when multiple threads access shared resources simultaneously. This can lead to unpredictable behavior and incorrect results. 2. Another common issue is deadlock, where two or more threads are blocked, waiting for each other to release resources. This can result in a program freezing or becoming unresponsive. 3. Starvation is another issue that can occur when a thread is unable to access a shared resource because other threads are constantly accessing it. This can lead to poor performance and decreased efficiency. 4. Inconsistent state can also be a problem in a multi-threaded environment if proper synchronization mechanisms are not in place. Threads can modify shared data concurrently, leading to inconsistent state and incorrect results. 5. Finally, incorrect or excessive use of synchronization can result in performance issues in Java programs. It is important to optimize synchronization to achieve maximum performance. In this slide, we will introduce the concept of concurrent collections in Java for efficient thread-safe data storage. Concurrent collections are a specialized type of collection that provides thread-safe access and modification operations. They are designed to be used in multi-threaded environments where multiple threads may concurrently access or modify the collection. Concurrent collections use various synchronization techniques such as locks, atomic operations, or concurrent data structures to ensure thread safety. They are particularly useful in scenarios where high concurrency and performance are required, while also maintaining data integrity and consistency. Now let's take a look at a code snippet to better understand the concept of concurrent collections in Java for efficient thread-safe data storage. In this example, we import the Java util concurrent hashmap class, which is a concurrent implementation of the map interface in Java. We create a new instance of the concurrent hashmap class and add key-value pairs to it using the put method. We can retrieve a value from the map using the get method and modify a value using the put method. We can also remove a key-value pair from the map using the remove method. Finally, we iterate over the map using a for each loop and print out each key-value pair. This code demonstrates how concurrent collections can be used to safely store and manipulate data in a multi-threaded environment. Synchronization in Java is the process of controlling the access of multiple threads to shared resources. It ensures that only one thread can access the shared resource at a time. Synchronization prevents race conditions and data inconsistencies that can occur when multiple threads access shared data simultaneously. To achieve synchronization, Java provides built-in mechanisms such as synchronized blocks and methods. It is important to use synchronization carefully to avoid deadlocks and performance issues. Here's an example of synchronization in Java. The example class has a private count variable. The increment method is synchronized, which means only one thread can execute it at a time. In the mon method, two threads are created and started. Each thread executes the increment method 1,000 times. After both threads have finished executing, the final value of count is printed. In Java, synchronization is used to control access to shared resources by multiple threads. This means that only one thread can execute a synchronized block of code at a time. Synchronization is important in Java because it helps prevent race conditions and data inconsistencies. It ensures that threads can work correctly and safely when accessing shared data. Using synchronization can improve the performance and reliability of multi-threaded applications. To synchronize a block of code in Java, you can use the synchronized keyword. You can synchronize on an object or a class. Synchronized methods are methods that are synchronized on the instance of the class. Synchronized static methods are synchronized on the class itself. You can also use synchronized statements to synchronize a block of code within a method. In Java, you can use the synchronized keyword to synchronize a method. This ensures that only one thread can execute the method at a time. Here's an example of a synchronized method in Java. You can also synchronize a static method in Java by using the synchronized keyword with the static modifier. This ensures that only one thread can execute the static method at a time. Here's an example of a synchronized static method in Java.